So after this chapter, we'll only have 2 more chapters we'll need to cover before the end of the term. And one of them's counters and one of them's timers. So basically, if we lay out the rest of the term, we'll be in lab starting next class. It looks like Chrome works okay with the new Blackboard, so I'm trying to get Chrome installed on the computers down here. If I can't get it installed, then we'll have to do lab here to start off with, and then toward the end of the class, we'll have to go over to what we did last time and take the test. But hopefully I can get it done. It looks like Chrome's going to work okay on the ones that I've got it on so far. You know. And then we'll come back the next class and we'll go over the test, and and the test will consist of 2 parts. We'll have an online part, a Blackboard part, and we'll have a part that you'll take home similar to the first test. And then you'll have to bring back part 1, right, and give me that. So the next class after that, we'll come in, we'll go over the test and show you how I came up with your grade, and then we'll go to lab after that. And then the next class, we'll finish up our lectures on counters and timers, and then we'll be in lab until we take test 3. Test 3 we'll give at the start of class. And why I give test 3 at the start of class, I think we can go over it before you go home, right? Understand? Now we're taking test 2. Assignment PT1 is due before test 2 by the start of class. So that's what we do. We'll go down there, and when the class starts, whatever the highest grade you have, that's what you'll get for that assignment. Okay, so that means if you take it once and don't get a good score, you can keep taking it and it keeps your highest grade. So that means if you make 80 on it one time and make 77 on it the second time you take it, then you get to what? You get to 80, so it keeps your highest grade. And that's what you get on that assignment. And then, of course, you can take it as many times as you want to. So what you probably need to do is do it, right? You understand? And then when we take test 3, assignment PT3 is going to be due before test 3. And then assignment PT3 will be before the final exam. So if you study these, and all the final exam is just questions off the 3 tests. So I wish my college professors would have done that for me. Give me a copy of the file. So basically, you got a copy of the file, you just don't know which questions I'm going to choose, right? So that's about the layout for the rest of the term. Chapter 7, this is logic. This shouldn't take a whole lot of time. Hopefully this makes sense. So what we're going to do is we're going to look at nots, ands, ors, nands, nors, and I need to unfreeze my display. And we're not going to look at Boolean equations in this. Well, we do need to learn what we call truth tables. And this is a bunch of garbage that's in the textbook. And we'll look at what we call common. So we have 5 basic logic functions. They're nands, ands, ors, nots, nands, and nors. And then we have 2 combinational logic circuits, which we combine logic to get a more specific application. And this is called exclusive ORs and exclusive NORs. But out of these 5 basic gates, all digital devices are made out of these. Of course, now we actually simulate these with programs. 5 basic gates: nots, ands, ors, nands, and nors. And the combination we'll look at is exclusive ors and exclusive nors. And we're not going to look at sequential logic in this class. So Boolean expressions, and we'll look at this. Boolean is a type of math that deals strictly with logic. You're not doing addition and you're not doing subtraction. So basically, you design a circuit and you set up what we call the Boolean equation. And then one of the things that you use in algebra is what we call equation reduction. Anybody had algebra? So you start off with an equation that's just big, and then you start reducing it down, and then you end up with a lot smaller equation. But what we're doing with Boolean and algebra is different math, different logic operations has a way we can represent that mathematically. And then what's nice about this is we can reduce it. A lot of the rules that you learned in algebra would apply to algebra, but it's pretty nice. And all we got is and and orders and odds and ends. We don't have squares. We don't have square roots. We don't have any of that other garbage that you have to learn in algebra. But in there, if we take an equation of a circuit and reduce it, we're literally making the circuit smaller. And when you take digital, we'll play around with it a little bit. But this would be in design. But what we need to understand is in digital, we can represent digital information different ways. Here we use a lot of true, false. In Boolean equations, we're going to use ones and zeros. So here when we say true, we'll usually represent that with a 1, and false, we usually represent that with a 0. Does that make sense? When we look at these tables, what we call function tables. But as far as learning reduction in this class, we're not going to do that. We're not an engineering class. We're not engineering. We teach basically to take something that's already been designed and fix it, right? So we use lows and highs. We use trues and false. We use zeros and ones to represent these things. So a high represented by the presence of voltage or a potential on an input, usually represented by 5 volts, and that's not true. Most of our PLCs now either use an AC voltage or a DC voltage. And originally we deal with higher voltage, but over time we found out that most of our inputs on our PLCs were going to be dealing with lower voltages. And what advantage does low voltage have over high voltage? You have safer. You know. So most of the time in your control cabinets, it's either going to be 20s, like your air conditioner, your heater. All the blower motors and fans out there run off 240 volts. That brings 240 volts up to your control. That brings 26 volts up to you. Why? Because if they go 240 volts up to your thermostat, and there's a lot of people being killed by their thermostat, right? You understand that? So usually our control circuits are low voltage. But in digital, inside the PLC, inside the computer, this is true. Uses about 5 volts to represent a 1 and 0 volts to represent a 0. In most PLCs, it's either going to be a voltage is present or a voltage is absent. Right now, the most popular voltage on inputs is 24 volts, DC. So this is called a truth table. So a truth table gives us all the combinations we can put on a logic circuit and how the output responds to that. So what they're saying is I could take this. So the OR function, we represent that with a plus. The AND function, we represent that with, like we do, multiplies. Normally, he's using apostrophes, but most of the time, we used a lot of things before we had a printer that could do this for us. So this says we get a 1 when A is what? When A is a 0, B is a 0, and C, I'm sorry, we get a 1 when A is a 0, B is a 0, and C is a 1. And then it says we get a 1. So all we do on our math equation is we look when the output is what? Is true. Then if we can set up a math equation, so right off the bat, I can see this is going to reduce. How can I know it's reduced? How do I know this is going? How would I know? What do you look for in algebra to see if an equation will reduce? Terms. So I see I got a not A, right? I've got a BC, I got a BC, so I can see like terms in there. So I know right off the bat this circuit can actually reduce. And then a lot of the rules that you learn in algebra would be the same. So we split them out, we move them around. But what's real cool with this? Once I get an equation, and if we reduce this, then the overall circuit would reduce. And I don't know if they're going to show you the circuit. So this is the actual circuit. So, and I've reduced it for you. So this was the circuit. This is the actual circuit using symbols. So this B shape, this is a symbol for an AND. This is a symbol for an OR. And this is a symbol for a NOT. And that was the actual circuit that the truth table did. And then I broke it down to this circuit right here. A and B, A, B, OR, not A. So I'd come over here and put a not right here. So that's my final circuit. So in my mind, I saw this, but in actuality, this circuit right here does exactly the same thing. And this is the power of Boolean algebra. But if you look, the techniques are basically what? The same that you learn in algebra. So this is nice to know stuff. So we're not going to reduce these. But these are gate symbols. These are not colored in, by the way. This is the symbol for an AND. This is a symbol for an OR. This is a symbol for an AND. This is a symbol for a NOT. So AND says needs at least 2 inputs, 1 output, and it says all. So it says all these inputs have to be a 1, has to be true before the output goes true. This says if I put a true in, I'm going to get a what out of it? False. If I put a false in, I'm going to get a what? True. So it says, get this to go true, not A, which means this has got to be low, which gives us high, right? And C, we get this right here to go true. Or says any. So if any input is true, the output would be what? True, yeah. Are we playing with our phones in class? Okay. Even though I know you are. So a NOT gate, output inverse of input, sometimes called an inverter. Function is simulated with electrical circuit. So here's the truth table. So a truth table is going to use 1s and 0s, right? So this says if my A input is false, the output would be what? True. And if the input is true, the output would be false. So all this is going to do is just invert it. These guys will always have 1 input. And 1 output. You already know this, man. You're playing with your phone back there. You're playing with you're listening to music instead of listening to me. You already know this. Okay. If you do, you can teach it for me. Okay. At least two. It could have multiple inputs. Got to have at least two. So how many different combinations can I put on three different inputs? They're binary combinations. 8. How'd you come up with that? 2 to the third. Good. So that means if I call the inputs A, B, C, A, B, C, and I call my output Z, usually on a function table we'll assign lower letters for the inputs and higher letters for the outputs. And then I just count. So that'd be 0, 1, 2, 3, 4, 5, 6, 7. Okay. So when we see this symbol, we're going to use the term all. All highs or all ones on the inputs would give me a 1 on the output. So is this all ones? 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 That all ones? Yeah. So that's an all. That's what we mean. Got to have at least what? 2 or more. Got to have at least 2 or more. We don't get much further than this because the number of input combinations varies with the power of 2. So if I added one more input, then I would have 16 combinations. So these truth tables only work real well for just to show that you understand the logic. So we have 2 inputs. That means four inputs, 4 combinations. We have 3 inputs. That would be 8. 4 inputs would be 16. 5 inputs would be 32. So now the truth table gets too cumbersome to even use when you understand what? If you understand this right here, all, you can say highs, or you can say what? Ones, or you can say truths, equals a what? Equals a high out. Now, if you learn that, you got AND gates. So let's say I got 15 inputs. All the inputs have to be high for the output to go what? High. Or all inputs have to be true. So probably learning the expression on these would be better than learning truth tables because the expression accounts for everything, right? Okay, this is an OR. Any one, or what I could say high, or I could say true, equals a true out. Is this any high? No. Is this any high? Is this any high? Is this any high? Okay, so what did our output do? Okay, the output, so if any input was true, the output is true, right? So anytime I see this symbol right here, we're going to use the what term what? Any. That makes sense. Now this says all highs equals a low out. Don't worry about that. So here's all highs, and what did I get out? No. How many inputs could this thing have? How many inputs can this guy here have? 2 or more. All of them says all highs in equals what? High out. So anytime you see this symbol right here,
Anytime we see the symbol right here, we're going to start off with all, right? So what would this guy right here say? Any,
It's any. By the way, this is the Boolean equation, but we're not going to require that in this class. There's a programming language called function block diagram, which you program with these symbols, but you don't use these are ANSI symbols. You use IEC symbols. When you learn those symbols, and you access.
So what did we look at so far? We looked at a not. We looked at an and. We looked at a nor. I'm sorry, a nan. And we looked at a nor. Are we okay? This says, you can say it either way. Low end equals high out. High end equals a low out. This is the only one that has one input and one output. An and has at least what? Two or more. An and has two or more. A nor has two or more. Okay. Any questions? So you're going to have the symbol of the test, and you're going to have to identify the truth table for the symbol, for the logic. And you'll be says yes. You've already had digital. Oh, Kelly, you're in Kelly's this time. This is an exclusive test. It will only have two inputs. This is not an OR. If it was an OR, it wouldn't have this ghosting input like that. This will only have two, no more, no less. These are our comparators. These tell us when the two inputs are the same, or the two inputs are different. This is an exclusive OR. Well, OR says any high. Well, that means, is this any high? Yes, it is any high. No, no, OR says any high is low. This is notice it's got let's go back to the OR. Any high. Now, somebody wants to call it all high. This we're trying to say all means only one combination. I have one output. This I have three outputs. Give me one. So that's not all. That's a lot. Okay. So look over here. 0, 1, 1, 1. This is an OR. This is an exclusive. 0, 1, 1, 0. This is different. Now look at this thing. If the two inputs are the same, so here's the same right here. So there's the same right here. What did I get out? Here they're the same. I got a what? Here they're different. So if the inputs are different, we get a 1. If the inputs are the same, we get a 0. What this is showing us what we get if they're not equal. So right off the bat, if I take a meter or something, look at this output is a 5, and I know they're don't care which one they're right.
No.
This is an OR. This is an exclusive OR. So I might have covered that up when you wasn't looking. See a little, yeah. This one can have 2 or more inputs. This only has 2. It's a comparator. It's saying, okay, are the 2 inputs equal? Or are they not equal? This is an exclusive NOR. Can you look at the truth table? So this is just opposite. So what's the relationship between this one and that one? They're the same, right? They're either both zeros or they're both ones. This says if they are different, I get a 0 out of it. So this is an exclusive, since it's got the bubble on the output, this is an exclusive NOR. But up here, this is the way we abbreviate it most of the time.
These are comparators. How many inputs will it have? We got this instruction. So like I said, there's a programming language called, and it's not the only language supported by RSA 500 is Ladder. We started developing these things, and that's advancing. They wanted more people coming up with different trades. So people have to people that can't go through computer science and learn Pascal and see what they program skills. There's some other which gives you more ladder. But also gives you a program that helps you come up through different disciplines. It's all determined by your applications. I can't get RS Logic 5000 to run on this computer anymore, but and we're not going to reduce in this class. So I'm going to give y'all these. This is the symbols here, and we just symbols here. These are the IEC symbols. So this function block diagram uses these symbols right here. International Electrotechnical Commission. So these are international symbols. These are symbols that we use mainly. Something fancy stands for. I know. Natural stands. So these are symbols we use over here. PLCs are not American anymore, right? They're what? They're international. So these are the symbols that we use in programs. But they're still ANDs, they're still ORs, they're still ANDs, they're still ORs, there's AND. Now notice it's got the little triangle in on the output that indicates the low active output. Exclusive ORs equal to a 1, equal to a 1. I would go here. That's the symbols we use around these. So I'll give you all these out in case you ever run into them, but and we're not going to deal with cordon off maps, so we're not doing any design in here, guys. So what we're going to do is go all through all this stuff right here. Nancy loves cordon off maps or K-map. I like Boolean algebra. I'm a math person, so but they're just as cumbersome as truth tables, and they use great code to count. They're really weird, but you got to have a cell for every combination. I mean, once you get over 4 combinations, you got 16 cells. once you go one more, you never two tails. So K-mounts are just as cumbersome as one. It's true tails, yeah. But she loves them. I like algebra. I like math.
So we're not doing any design, so let's skip over real quick and get to the actual ladder logic that we use to implement these. So this is the way we implement this logic with relays. So what would be a not? First of all, we'll do the low active first. So I'd come over here and I'd do this, and these are just going to be contacts, and they're going to be controlled by something. They're going to be controlled by something different. And this could be so what logic would this be right here? How did you come up with that? That's exactly right. All the contacts have to be closed before the output goes through. So as soon as I say all, it's some type of what? It's either and or an and. So exactly right. Good job. So this would be an all, right? Everybody see it. How many contacts can I have? At least what? 2. How many could I have? A lot. But anytime you see these normally open contacts in series like that, they're all going to be controlled by something different. So that's why I put ABC. It could be relay, it could be a push button, it could be all kinds of things. External, right? Understand that. This is an and. I'm using 3 just to make sure y'all understand this. What logic would this be? Because I use the term what? Any. If any contact closes, then the output of this circuit would be true. That makes sense? So any. If I start off with any, I shouldn't have put this. This is the what? Any. Are we okay? Any questions there? Any questions on the any? Okay. Y'all got this? Can I erase it? Now, your NANDs and your NORs is what's required to make its output go false. So ANDs and ORs are what's required to make the output of the logic go true. Not NANDs and NORs are what's required to cause the output of the logic to go false. So this guy here starts off true. So what logic would this be? Yeah, there's only one of them. So this is a not. What would this be? So this guy here starts off true, and I use the term any. If any contact opens, the run goes false. So as soon as I say any, it's going to be either an and, it's either going to be a what? You know. What do you mean? Yeah, but they're normally open contacts.
And this gets people, this is where people have a problem. They learn the and. And anytime they see contacts that are in series, they want to call them and they don't pay attention if they're not normally closed. So as soon as I say, so and, nots, nands, and nors are what's required to make the output false. Ands and ors are what's required to make the output true. So this guy here starts off true. And if any contact opens, the rung goes false. And as soon as I said any, it cannot be an and. It cannot be an and, because if it's that, it would be what? I would have to say, oh, here I say any. Any contact opens, the rung goes false. So this is a what? Nor, yeah. But what people do, they jump on the and. But remember, the and is what? Is normally open contacts. This is a nor. I'm just going to put 2 up here, guys, because I'm running on stage. They're going to be controlled by different inputs, right? So what do I say here? So this thing starts off true. What's required to make it go false? All these contacts have to open before the output goes false. So this is a what? That's an and. But the problem is they learn the or, and they say, okay, contacts in parallel or, but those are not normally closed contacts in parallel. Those are what? Normally open. So nots, nands, and nors are what's required to cause the output to go false. Ands and ors are what's required to cause the output to go true. So as soon as I see normally closed contacts, I need to start thinking what? Not, nan, or nor. Not's easy because there's only one of them. And see, okay, what's required to cause it? Now, that output, and why is that? Because I could come up here and do this. And this could be C, and this could be D. So what we're doing is we're combining logic, right? You understand? So I've got a what? I've got a NAND feeding an AND. But this output right here, this guy here starts off true. This right here starts off what? False. So we can combine logic. We definitely can. So I'm not going to say what causes the rung to go true. It's what causes the output of the logic to go true or false. Are we okay? Okay. Got 2 more and then we're through with the lecture for this. Not that y'all have any questions. So we got to combine some stuff and end up with a gate. I'm going to call this AB, and I'm going to call this AB, and I'm going to do this. What logic is this? Now notice A and B are repeated. A, B, A, B. So whatever's controlling A up there is controlling A down here, and whatever's controlling the B up there is controlling the B down there. How do you know that? How did you stop for? Oh, you're looking at it in the book. Well, what does this start out? So both my inputs are in their state. Okay, so does it start off false or does it start off true? Okay. So what do I need to make it go true?
So I could close A. Can't say A or B because one of them's normally closed and one of them's already open, right? Understand? Yeah. So if I come over here and made this A true, then this right here would go what? And of course we got a path that goes through here. Everybody okay? And then if I come over here and made if I made B true, then this would close and this would open and the output would go true. All right. So what does this guy here start off as? Does it start off? So if the inputs are the same, what do we get out of it? Let's do this. So if they're the same, we get nothing. If they're different, we get a 1, right? That makes sense. So this is why this is an OR. So I look at it. What happens when nothing's going on? And we'll take the same thing. So this guy starts off what? True. And if the inputs are different, it goes false. So this is a so this is an exclusive NOR. And that's all 5 of them. I mean, it's all 7 of them. This is what we call a combinational because it's combining different logic, right? You understand that? It's combining, and here we're combining a NOR with an AND. So we call this a combinational circuit. And these are our comparators. Have you any questions? Anyone want to go back over? So we're going to have to identify these contacts for what they would be wired on the next test. Yeah. This is the way we would, I'm going to leave multiple contacts. Or programmed. You know, most of this logic is going to be programmed, guys. So we'll bring inputs and we'll hook our inputs up to an input port, and then we program these, right? So A, B, C, D. What's this? This is an AND. And that's the way they would be programmed, or that's the way they would be wired. In motor controls, we'd wire them. What we'd do on PLCs, if we're controlling them with an input, is we'd come over here and if I'm doing syncing and sourcing, we'd come over here and we'd take our inputs and hook them up over here. And how many do I have? Let's erase them. And this would be A, B, C, and then I would bring this in. So we have this hooked up. We have syncing inputs, right? And my actual input device would have to be wired to do wired sourcing. Yeah, I could take those same things and use this. So this is a what? And if I wire them in my program like this, then what do we have now? Yeah, we have a NOR. What's nice about a PLC, and this is why examine if open, examine if close, we can make a normally open push button act like a normally closed in our logic, right? You understand that? So what we're saying is I can take these three push buttons and I can program them to either be, so this is a what? But the actual instructions. This is the examine if open. So these guys right here are all open, right? So all these are going to be true. So it's still an OR. You understand that? And that's what's confusing about PLCs. Now, the only time we're worried about it is when I come over here and use this. When I say stop, what does a stop button have to be? It's got to be a normally closed push button. I'm sorry, it's supposed to be. You have some programmers don't do that. They love to use all normally open push buttons. And then one day when the wire breaks, they can't do what? They can't stop. But if I'm doing logic, then I can use normally open push buttons out here, but in my PLC program, they're going to be what? This is the examine if what? Open. Is this open? So that this would be true, that would be true, and that would be true. So it's going to be a NOR. So I have to push a button to make it do what? Make it go false. In fact, this is a little easier to see than trying to use normally closed push buttons. And then I would wire them like this. If I come up here and wire them like this, and I'm not going to put the letters, guys. Or I program them like that. This is normally open contacts. Yeah, good. If it's normally open contact, it's going to be a what? It's going to be either an and or an or. If it's normally closed contacts, it's either going to be a not, an and, or an or. So this would be a what? This is an and. And then this right here, one would be a what? Not. So yeah, does it make a difference how you connect them? Yes, it does. Or program them. So on a PLC, we wouldn't actually have the push buttons, right? We'd have a what? We'd hook it up to an input, and then we make it what we want it to be. The only thing we got to be careful with is these guys right here. So here we'd use an examine if close. Over here, if we want to make a normally open push button act like a normally open, a normally open push button act like a normally closed, we just use an examine if open instruction. These are examine if closed instructions, right? So here, this could be these normally open push buttons, but to make this run output false, I'd have to take all those three push buttons. I'd have to push them all in. I don't know if they're normally open, I don't know if they're normally closed, which makes it nice in PLCs. Except for stop buttons, we can use normally open push buttons everywhere, and then make our PLC just treat them like they're what? They're normally closed. So this is what's neat about a PLC, because now instead of me carrying all these different push buttons, I just carry a bunch of what? Normally open ones. But if it's a stop button, it's supposed to be a what? It's supposed to be a normally closed stop button. And that way, if the wire breaks, then whatever you're running will do what? Will stop. After that, that's the only time that's stipulated that you have to use a normally closed push button. It's for stops.
And if you got on a exclusive ore, if you see the staggered contacts like this this is the what? This is an exclusive ore. If you see them the same on both the top and the bottom, then this is an ore. We was taking the Siemens classes over in Germany. By the way, what's nice about all the Siemens classes are in English, so everybody had to know English. Which basically, English is the international language, right? Even pilots. So control towers have to talk what language? English. So that's one thing he threw the thing up there, and he was really shocked. He said, "We was talking about exclusive orders. He had a whiteboard up there and says, anybody can draw that." So, yeah. So he didn't think we could do it, but yeah. So believe it or not, guys, they got where if I raise my hand, they just skip over me. So true story. So that's the logic. That's the test, guys. This is everything that's going to be on test. Y'all got any questions? Everybody's got the review, right? What I'll do when we get down to the lab, what time is it? So what we're going to do when we start off, what we're going to do when we start off, so I'm going to let go. Not unless anybody wants me to help them with any of this stuff. If you don't want me to help you with it, then we'll let out early tonight. What are we going to do when we start out? I got to have it back. Where y'all going to go? We don't come in Wednesday. Straight to lab. We might have to go over there. If I can't get Blackboard working over here, but it looks promising, guys.